Hello everybody and welcome to the final video of your Physics 11 journey in our Octa schedule here. So we are going to look at thermal energy to finish off the course. I'm going to talk a little bit about thermal energy, temperature, heat. We'll talk about how heat kind of flows. But what I'm really excited to get into is the formula and the math because it's a lot more fun. So first of all, thermal energy is the total amount of kinetic energy and potential energy of the particles in an object. So we know, hopefully from chemistry or science 10, that as a material is heated up, the molecules start moving faster and faster, and that material generally expands. And so you're going to get, as you get more thermal energy, like the particles are going to have more kinetic energy. They're going to be moving around faster and faster. And that's what, that's why there's more thermal energy. There's more kinetic energy. Temperature is the average kinetic energy of the particles in an object. We will actually use temperature in the thermal energy formula. And then heat is the transfer of thermal energy. So heat will always flow from high concentration to low concentration by 3 different ways. Conduction, which is contact. So 2 surfaces contacting each other. Convection. You don't need to know this for the test, but it's good to know as a prerequisite knowledge. Convection is movement through liquid. And radiation. So we have no medium required. And this will happen until thermal equilibrium is achieved. So I always imagine if you're pouring a really hot liquid into a really cold liquid, obviously they're going to be at different temperatures, and we're going to get convection happening, so movement through liquid, and then we'll eventually reach a thermal equilibrium where both temperatures of the waters are the same, because the colder water will increase its temperature and the warmer water will decrease its temperature, and we'll find like a middle ground, if that makes sense. So the formula is EH, or I'm actually going to use ET, thermal energy, is equal to, I'm not sure what it is on your formula sheet. I don't have one handy, but we'll figure that out. MC delta T, where ET is thermal energy, and that is in joules, like all energy. M is the mass of our object. Mass is always in kilograms. C is the specific heat capacity. Specific heat capacity. And this is different for every material, and usually you're given this or finding it. And the units for this are super weird. This is joules per kilograms and degrees Celsius. Joules divided by kilograms degrees Celsius. And then this is change in temperature in degrees Celsius. So this formula can also be written as ET is equal to MC multiplied by, we know delta T is temperature final minus temperature initial. kind of the same thing there. Let's dive in and use this in a couple of questions. If I make a cup of coffee, there we go, let's not get distracted. If I make a cup of coffee by boiling 250 grams of water that is initially at 15 degrees Celsius, how much heat is needed? All right, so we need to know a couple of things. The specific heat capacity of water is 4,180 joules per kilogram degrees Celsius. And water boils at what temperature? Water boils at 100 degrees Celsius. You need to know both of those before we go in. So that means our T final will be 100 degrees Celsius. Our T initial is going to be 15 degrees Celsius. The mass will be 250 grams. So 250 grams multiplied by, we want to switch to kilograms, 1,000 grams in a kilogram. So when we do that, we get 0.25 kilograms. And we have the specific heat capacity of water already listed there. So our formula, ET is equal to MC T final minus T initial. And we can just plug everything in here. The mass is 0.25. Our specific heat capacity, 4,180. And we have final temperature of 100 minus 15. So I get 88,825. It's energy, so it's joules. Perfect. I got a tricky question here, so we'll talk a little bit about this. It's our last one. A 35, I think it is anyways. Yeah, looks like it. A 35 kilogram child goes down a 3.2 meter high slide. The child is initially at rest and moving at 1.8 meters per second at the bottom of the slide. If the slide is made of 12 kilograms of iron and all the heat is transferred into the slide, by how much does the temperature of the slide increase? And we have the specific heat capacity of iron being 460 joules per kilogram degree Celsius, sorry. And you can see here this looks somewhat like, or looks closely like a conservation of energy problem. So we have, let's do our little slide here. We have a kid sitting at the top. At the top, he's going to have a combination of kinetic and potential energy. At the bottom, he will also have a combination of kinetic and potential energy. However, so this is our initial. In the final, we have to also include thermal energy because we lost some thermal energy. So in the final, we have to include that because energy is conserved. So we can say E energy initial is equal to energy final. Initially, we're going to have kinetic energy initial plus potential energy initial. Final will be kinetic energy final plus potential energy final plus thermal energy. So the reason we have to do this is because we are trying to find how much the temperature of the slide increases. So we want to use this formula. And if we're using this formula, we know the mass of the slide. We know the specific heat capacity of iron. We're looking for delta T. So we need to find thermal energy. The only way we can do that is calculate the conservation of energy here. So let's look at this right now. If we make the bottom of our slide height 0, that means the potential energy of the kid at the bottom of the slide will be 0. It also means that the kinetic energy, so at the top of the slide, the child starts at rest. So the kinetic energy at the top will also be 0. This makes our life a little bit easier because now our formula is potential energy initial is going to be kinetic energy final plus our thermal energy. And now we can just solve. MGHI is equal to 1/2 mv final squared plus ET. So we can subtract that term from both sides. We could have done that before we expanded. And we get ET is equal to MGH initial minus 1/2 mv final squared. All right, let's plug some things in. What is the mass of the child? 35 kilogram child. 35 multiplied by 9.81. The child started at a height of 3.2 meters. Subtract 1/2, again, a 35 kilogram child. And how fast is the kid going at the bottom? That's 1.8 meters per second, and we'll square that. Let's punch some numbers in. 35 multiplied by 9.81 multiplied by 3.2. That gives us 1,098.72. Subtract 1.8 squared multiplied by 35 divided by 2. Subtract 56.7. So that means our energy thermal is going to equal 1,033 joules. Now we can carry this back up and plop it in here. So we can say, well, we're looking for delta T. So now I'm going to divide both sides by MC, because we're looking for how much the temperature changed. So we don't need to find T final or T initial. We can just find change in temperature. Cancel those out, and I've got my change in temperature is equal to ET over MC. ET is 1,033 joules divided by our mass of our slide was 12 kilograms multiplied by the specific heat capacity of iron, which was 460. So 1,033 divided by 12 multiplied by 460. And we get an increase in temperature of 0.19 degrees Celsius. So that's how much the temperature of the slide changed from the child sliding down it. We are going to look at problems where we place like a hot piece of metal into some water and we find that equilibrium temperature, but we'll cover those more in class. That's it. That's the final one. Thanks for watching. Don't forget to like and subscribe.